Thank you very much, Aisha. Thank you for inviting me here. So inverse problems is not my, I haven't been working in inverse problems for a long time. And so I really appreciate making new connections in this area. So it's really a pleasure to speak at specialist seminars on this. Okay, so this work is joint work with Franciszek Sztampak from Prague. He's uh, um, a bit younger than myself, working also in spectral theory. So let me start. So first, so I should say that the main word here perhaps is non-self-adjoint, which is the non-standard aspect of our work. But I will start by giving a background on self-adjoint, on standard self-adjoint theory. So for the first maybe 20 minutes, everything I will say is very well known, very classical. And just to give a gentle introduction. So who are these Jacobi matrices? So these are tridiagonal matrices. So you have something on the diagonal and something off the diagonal, on something on the line above and on the line below the diagonal. And so these A's are supposed to be positive and the B's are supposed to be real. And we should think of this as an operator acting on this little L2 space of sequences labeled by non-negative integers. So let's assume that these sequences A's and B's, they are uniformly bounded. And it's easy to see that this is equivalent to this matrix as an operator on this L2 being bounded. So we will talk about bounded operators in this talk. So in addition to being bounded, we want this J, this Jacobi matrix, to be self-adjoint. And it's clear to see that this means under this, so it means that Bn must be real. And if I write A here and A here without complex conjugation, that forces A to be real as well. So if I assume these assumptions, then this matrix J is a bounded operator on L2. So now let me discuss this condition a little bit. By the way, hope you can see my pointer, right? When I'm doing this, you can see, right, where I'm pointing.
We can see. Mm-hmm.
Yeah, okay, fantastic. So I want to comment on this condition. So let me split it into kind of two steps. The first that it's non-zero, second that it's positive. The fact that all these A's must be non-zero can be understood like this. Imagine, for example, A1 vanishes. Imagine A1 is 0. Then our matrix basically splits into two blocks. There is this block, the first 2 by 2, the top left 2 by 2 matrix, and then it's orthogonal sum with everything else. And then we don't want to allow this splitting. We want everything to be kind of linked. And therefore, we want these non-diagonal terms, off-diagonal terms, to be non-zero. That's kind of non-degeneracy. So after we have said this, we have to choose a sign just to agree. Either they're all negative or they're all positive, or prescribe any sequence of signs. And that is purely convention. So it is customary to assume that all n's are positive. It's a natural assumption, but I could have given the same talk with an being negative, for example. So this is just a normalization. Okay, let's move on. So now I will denote by E naught the first element of the standard basis in L2, and it plays a distinguished role in the theory of Jacobi matrices. So here is the fact that this E naught, it is a cyclic vector for this Jacobi matrix. So what does it mean? There are two definitions of cyclicity, whichever you prefer. There is a dynamical, that means that you look at all the powers of J, apply this to E naught, and consider the span, and the closure of the span must give you the whole L2. That's the dynamical definition, and this is probably the most common. But there is also a spectral definition. So the spectral definition naively means the following. Imagine there is no continuous spectrum. All the spectrum of this matrix J consists of eigenvalues. Then the spectral definition of cyclicity says all eigenvalues must be simple, and if you have an eigenvector, then this eigenvector cannot be orthogonal to this distinguished vector E naught. Okay, so all of these inner products are non-zero for all eigenvectors. And of course, this is, remembering who is E naught, this is just the zeroth coordinate of any eigenvector. So why is this? Why is E naught cyclic vector? So let me give a kind of naive explanation. So suppose we have an eigenvector x with an eigenvalue s. So for some reason, I will denote these eigenvalues by s, but that's an eigenvalue. And so let's write down the eigenvalue equation. So remembering what is j, I apply j to x, and I get this kind of line by line. I record these equations. So first equation, second equation, third, and so on. Then looking at the first equation, it involves x naught and x1. So assume, to get a contradiction, that x naught is orthogonal to this vector x. That means the x naught coordinate is 0. And therefore, from the first equation, we see that x1 must be 0. Then going to the second equation, we see x1 and x naught be 0, then x2 is 0, and so on and so on and so on. And so the whole thing vanishes. And that's obviously, we don't want this. So it's a contradiction if we started with an eigenvector. So this shows that E naught is a cyclic vector. Okay. So now let me discuss, I'm slowly getting to inverse problems, but before inverse problems, we have to understand the direct problem. So what is the spectral measure of this Jacobi matrix? The spectral measure is defined in the standard way. So you take the characteristic function of an interval, so apply this function to J and take the inner product, consider the quadratic form of E naught. So these angular brackets in my notation, this is just the standard inner product in my little L2 space. And so this defines a measure, and we call it the spectral measure. Alternatively, if we integrate with some continuous, for example, function f, then we see that the spectral measure is defined by defining all of these integrals as these inner products. So for example, you can think of f of j being powers of j. Then it becomes much more concrete. On the right hand side are very concrete expressions. You apply powers of the matrix to E naught, and this should give you moments of the measure mu. So let's discuss this spectral measure. So for example, if J has a purely discrete spectrum, so just eigenvalues sk with eigenvectors xk, then this spectral measure is just the sum of point measures sitting at these eigenvalues with some weights. And these weights are precisely these squares of these inner products, xk, k is the kth eigenvector, with E naught without distinguished vector. Remember that we said the cyclicity enforces that this is non-zero. And so these weights mu k are non-zero. Now, so cyclicity, so sort of grown-up version of cyclicity, if we don't want to assume any particular a point spectrum, if it's just a general spectrum, then the proper version of cyclicity can be phrased like this, of spectral cyclicity, that if this measure vanishes on some interval, that means that the whole of this operator also vanishes. In other words, that there is no spectrum on this interval delta. So in other words, by taking this inner product, we are not missing any part of the spectrum. Okay, so from some kind of abstract operator theory, it follows that from this cyclicity, it follows that our operator J is unitarily equivalent to multiplication by the variable S in L2 of mu. L2 of mu in my notation is just a real line, L2 on the real line with this measure. And we are considering an operator multiplication by the independent variable in this L2 of mu, and J turns out to be orthogonal, unitarily equivalent to this operator. So mu is really a good descriptor of spectral properties of our operator. And so finally, the direct spectral problem is the map from J to the measure mu. Okay, so if the spectrum is discrete, you can think about it like this. From the matrix J, we go to the set of eigenvalues and to the set of these normalizing constants, as they sometimes called in different settings. But the measure mu can be arbitrary. It may have some continuous part, and then it is what it is. It's a measure. Okay, so now let's discuss the inverse problem. Okay, so here is the standard theorem, which goes back, classical theorem, which goes back to, I guess, people like Hieser, Crane, and so on. So it's a really classical statement. So first of all, the matrix J, Jacobi matrix, is uniquely determined by this spectral measure mu. Secondly, surjectivity of the spectral map, which means that all, basically, in simple words, all spectral measures mu are possible. More precisely, what does it mean? Suppose we have a probability measure mu with bounded infinite support on the real line. So what does it mean? Bounded means, bounded means bounded. It's in some subset of some bounded interval. And infinite support, we don't want to allow measures which are finite linear combinations of point masses, because this would lead to trivial situations where our Jacobi matrix is finite. If you have n point masses, then your Jacobi matrix is n by n, something like that. So if we have such a probability measure, then there exists a bounded Jacobi matrix, so a Jacobi matrix of the class that I described on the first slide, such that mu is the spectral measure for this matrix. So in other words, this theorem encompasses two statements, that this spectral map is an injection, right? So the mu is uniquely defined as J, and that it is a surjection, that all measures mu are possible. And so we have a bijection between Jacobi matrices and these measures. Okay, so one may ask, how do we actually invert this map? How do we reconstruct from the measure mu Jacobi matrix J? So this is related to standard theory of orthogonal polynomials. So in the theory of orthogonal polynomials, they kind of view what we probably say is an inverse problem. They look at it as a direct problem. So in orthogonal polynomials, the logic is as follows. You start from some given measure mu. You consider this L2 space, L2 of mu. Then you consider the functions 1, s squared, and so on. So s is my notation for independent variable in this space. So if you're more used to x, think of x, right? So these are just powers of the independent variable. And so these are functions in this L2 of mu. And we apply the Gram-Schmidt procedure to this sequence. Then we get a certain sequence of polynomials. And it turns out that they satisfy three-term recurrence relation. So for example, the first polynomial P1, if you multiply it by this independent variable s, you can expand it as a linear combination of P1, the previous one P0, and the next one P2. Okay, and so if you write down this whole chain of equations, then you get some coefficients A's and B's, and these are precisely the A's and B's that we are looking to reconstruct. So one can prove that this procedure is that precisely inverts the spectral map from J to mu. So I've described the classical self-adjoint inverse problem. Now I'm going to the main topic of the talk, the non-self-adjoint Jacobi matrices and the problem for them. So this is the same matrix, the same picture as before, but we have different conditions on the coefficients A and B. So A's are still positive, but B's we allow to be complex. Okay, B's we allow to be complex. And I will just denote by this J plus the set of Jacobi matrix of this form, where I assume boundedness as before. So the boundedness of coefficients implies that this J as an operator on little L2 space is bounded operator. But of course, because on the diagonal we have complex numbers, in general, it's non-self-adjoint. So here, let me again comment on this condition. So the symmetry is essential. It's essential that here A1, if I have A1 here I have A1 and not some other number. So this is kind of built into our construction. And again, it is essential that these ANs are non-vanishing for the same reason as before. We don't want this matrix to split into blocks. But positivity of an, again, is a normalization. So now we're working in the realm of complex numbers. I could say this AN could be any fixed sequence of complex numbers. We fix some phases. For example, they're all negative or all positive imaginary, whatever. But it is, of course, convenient to choose this standard normalization that they're positive numbers. Okay, and so now we want to do inverse spectral theory with this class of Jacobi matrices. So heuristically, because we allowed Bn to be complex, of course, we have more data in this matrix J. And so if we want to describe it through some spectral properties, we need more information. We need more spectral parameters. We need more data. And indeed, we will see that if in the classical case, our inverse problem was we reconstructed matrices from a measure, from a single kind of functional parameter. Here we will have two objects. There will be a certain measure and a certain function. This function will somehow encode the fact that these BNs are complex. Okay, we'll get to this in the next couple of slides. Now, I want to say one important thing, that although in theory we say it's a spectral problem, we are not really interested in the spectrum of this Jacobi, non-self-adjoint Jacobi matrix. So perhaps the original aspect of our work is that we are looking at a different way of parameterizing this matrix, and it's inspired by the polar decomposition. So remember that any non-self-adjoint operator, in particular this one, can be represented like this. You have absolute, you have modulus of J, which is square root of J star J. So that's a positive self-adjoint operator, positive semi-definite self-adjoint operator, and something else, something that is isometry or in general partial isometry. This is a bit like representing a complex number through its modulus and phase, okay? And so in some sense, our spectral parameters will have the same spirit. So we will have a measure which kind of describes modulus of J, and we have some function which we call phase function, which kind of describes this V. You should think of this as some sort of rotations in the Hilbert space. Okay, so I'll try to describe it in the next two slides. So let me describe how we set up this spectral data. So as I said, it will be a measure. We'll call it nu, and there will be a function. We call it a phase function psi. So let's start with the measure nu, spectral measure. So how do we define it? So it is a spectral measure, but it's not the spectral measure for J, but now for mod J. So mod J is a positive self-adjoint operator. Remember, it's square root of J star J. And we define the spectral measure for this operator corresponding to the same standard vector in node, the first element of our canonical basis in L2. Okay. Now, of course, this mod J, it's a positive semi-definite operator, so its spectrum lives on the positive half line, and so this measure also only lives on the positive half line. So as I said, equivalently, we can define this measure nu through this integral relation, or in particular, if you think of f being some power, then it's just this. It becomes a little bit more concrete, maybe, if you write it in this way. The moments of measure are defined in this way. Okay, so let's start with discussing the direct spectral problem. So this is what it says. The multiplicity of the spectrum of this mod J is less than or equal to 2. So remember that in the self-adjoint case, the multiplicity of spectrum of J was 1, but here it can be 1 or 2. And then the element E naught is of maximal type. So what is this? This is kind of generalization of cyclicity, I would say. It says the following, that imagine that our measure nu vanishes on some set. It means that on this set, we have no spectrum. So in some sense, it means that this, by taking this quadratic form, we do not miss any part of the spectrum of our operator. So a few comments on this, a few comments. So first of all, the multiplicity can be 2. It really can happen. For example, consider the self-adjoint case and imagine that your matrix J has eigenvalues lambda and minus lambda. Then when you take absolute value, they kind of are put together. You know, when you take the modulus function, it folds up the spectrum from the negative half axis to the positive. So you end up with an eigenvalue lambda, but of multiplicity 2. So next thing to say is that I said E naught is of maximal type. It's a concept that maybe not so obvious, but for example, if multiplicity equals 1, if multiplicity of the spectrum happens to be 1, if you don't have such examples, then E naught is automatically cyclic. And this condition automatically means cyclicity. And let's discuss what's going on if mod J has simple discrete spectrum. Then it's interesting that you have this kind of eigenvalue equation with a twist. So if Sk are the singular values of J, in other words, the eigenvalues of mod J, then you have this eigenvalue equation, but with a complex conjugation on the right-hand side. And your measure nu is again a point measure. It's based on these singular values Sk, supported on singular values Sk, and the coefficients will be the zeroth coordinates of the corresponding vectors. Okay, so to summarize, we've defined the first component of our spectral data, which is the spectral measure nu. Now I go to the second component of the spectral data, which is the phase function. The phase function. So what is it? So here I've just reproduced the equation from the previous slide, which is the definition of the measure nu. And now the idea is as follows. So don't look at the words for now. And I just want you to look at this equation and this equation. So I'm saying the following. Imagine now so these are all f of mod j. And now I add here j. Okay. So imagine that this function is a power. Then I have j star j to some power. And here as well, j star j to some power. And I add j here. So what effect will it have? So here, of course, because it's a 1 power of j, you expect to have 1 power of independent variable s. This is natural. But also you will have some phase. So this psi is some phase. So now let's state it more precisely. So this is a theorem, but we treat it as a definition. So the theorem says that there exists a unique function psi in L infinity with respect to this measure. Here, this S plays no role. It just says that at 0, this function is not well defined. So at 0, if nu had a point mass at 0, then S kills it. It's a small technicality, so don't worry about it. So so psi is a bounded complex valued function defined nu almost everywhere, and it satisfies this condition. So it's less than or equal to 1. such that we have this identity for all test functions f from some class. You can say polynomials or continuous functions, it doesn't matter. So as I said, it kind of shows the effect of applying j rather than mod j to this equation. So now let me motivate a little bit this definition. I want you to think of this function psi as some sort of rotations in Hilbert space corresponding to the actions of the operator j on eigenvalue s, or on singular value s. So let's look at some examples. So the simplest case, if mod j has a simple discrete spectrum, so just eigenvalues, then as I said on the previous slide, we have this eigenvalue equation. This is and this new case are the measure sitting at sk is this, and the corresponding psi, remember that this psi, it only lives on the support of the measure nu. The measure is supported on this point sk. So on this point sk, the value of this function is this kind of thing. It's an angle, right? It's a thing of modulus 1, right? Because I have some quantity divided by the absolute value of the same quantity squared. So you see, it's kind of suggests that this is some sort of angle related to the related to relative position in the Hilbert space between the kth eigenfunction and this vector E naught of the standard basis. So let's look at some other cases. So if J happens to be satisfy this commutation relation, this is called normal, right? So this is such operators in the Hilbert space that commute with the adjoint are called normal. If this happens to be true, it's a very special situation, but imagine this is true, and mod J has simple spectrum, then in fact the polar decomposition of J is precisely what you expect it to do, what you expect it to be. So there's mod J and this psi function. So psi function is precisely this angle. So it will be of modulus 1, and it will precisely describe these rotations affected by J. Okay, but in general, it may not be equal to 1. It may be less than or equal to 1. And so in general, it's hard to describe them intuitively, these functions, these rotations, psi, whatever they are, but it's a well-defined quantity. This is a small remark just to say that if you have any operator whose matrix is symmetric, so T is transposition, like our Jacobi matrix, remember it's symmetric with respect to transposition. So if you have any operator like this and any vector that satisfies this, it's real, it has real coordinates, then the same theorem is true. So it's nothing mysterious, this theorem, it's quite simple. Okay, so finally, we are coming to the main result, half an hour into the talk. Okay, so we have, remember that J plus, let me go back. So this J plus was my notation for the set of Jacobi matrices that are bounded. The off-diagonal elements are positive, and the elements on the diagonal are complex. So I just want to have notation for this class of matrices for convenience of stating my results. So back to the main result. So we are saying that any Jacobi matrix of this class is uniquely determined by this pair, the spectral measure and the phase function. That's uniqueness. Moreover, more surprisingly, we have surjectivity. So suppose we have a probability measure on positive half line with bounded infinite support. So remember, infinite support means it does not reduce to finitely many point masses. suppose psi is any function in L2 with respect to this measure, and it satisfies this. So it's less than or equal to 1, almost everywhere with respect to measure nu. Then this pair, the measure nu and the function psi, is the spectral data for some Jacobi matrix of our class. In other words, the map from Jacobi matrices to this pair is a bijection. So we get everything, all the spectral data in this class. Okay. So now let's consider some special cases. Maybe any questions maybe at this point. So this is kind of my main result, the highlight of the talk. If there are any questions, I would like to explain.
From anyone? It doesn't look so.
Okay.
Okay.
Okay. So let me continue. So let's consider some special cases. So because we have this map from J to these spectral parameters, it is natural to ask, how do you describe special classes of Jacobi matrices in terms of these parameters? Okay, and this is precisely what we say here. So for example, if Jacobi matrix is self-adjoint and positive semi-definite, then you kind of expect these angles to degenerate, and this is indeed the case. So we say that this J is positive semi-definite if and only if this angular function just degenerates to identically being to 1. All of this is nu almost everywhere. Psi is only defined, nu almost everywhere. Secondly, if the J is self-adjoint, if and only if this parameter psi is real valued. So this is where we're back to the self-adjoint world, no complex numbers, these are real parameters. Next, maybe less predictable perhaps, this matrix J has zeros on the diagonal, so if we require, remember AN are off diagonal and BN are on the diagonal. So these BN are all 0 if and only if the function psi, this phase function, vanishes identically. That's maybe less obvious. Finally, mod J has simple spectrum. Remember that it has, in general, it has spectrum of multiplicity at most 2. So sometimes it is 2, sometimes it is 1. We say it has simple spectrum if and only if mod psi function is 1. So if it is simple spectrum, then really it is, this psi is really rotation. If spectrum has multiplicity 2 somewhere, then at these points this psi is less than 1. There is something more complicated going. Okay. So now it's natural at this point to ask the following question. Imagine we have a self-adjoint matrix J. Then we have two inverse spectral problems. The traditional one, which I described in the first part of my talk, and this new one where you think of mod J and the phase function. So then you can ask, what is the relation between these two parameters, the standard measure mu and this measure nu and psi? Okay, so informally, you should think about it like this, that if a matrix J has positive and negative parts, when you take absolute value, you kind of fold them together. This absolute and the negative semi-axis folds up onto the positive one. And so in this case, you need, so this measure nu has information about both positive and negative, about this mu being both the one supported on positive and negative semi-axis. And psi tells you how to unfold back this, this folding. Okay, so in more precise terms, it's like this. Let's use tilde to denote a reflected measure, right? Reflected with respect to 0. Then we say that this mu can be unfolded from nu as follows. So this is the mu on the positive semi-axis. You take 1/2 of 1 plus psi. And on the negative semi-axis, up to this reflection, it's 1 minus psi. So psi tells you how to unfold. Okay, there is some special thing going on for 0, but that's maybe less important. Okay. So at this point, let me go back to the self-adjoint case for a second. So remember that I said that if we, in the self-adjoint case, if we want to reconstruct the matrix from the measure, we do it through these normalized orthogonal polynomials. We start with L2 with respect to the measure mu. We consider the powers of S. We apply Gram-Schmidt. The corresponding polynomials satisfy three-term recurrence relation, and this gives us the coefficients an and bn. So it turns out there is something similar going on in the self-adjoint case, but less obvious and with some twists, I would say. Okay, so first of all, I need some notation. So if you have some polynomial, it should be, sorry, this is a typo. So this should be P, okay? Let's say if you have a polynomial P, we denote the even part like this by P even, and the odd part like this by P odd. So that's clear what's going on. So now, if suppose we are given these spectral data, we have a measure and we have a function psi. Then we define such a funny functional. It's a it's a bilinear functional on two polynomials p and q, and this I use it denoted by these square brackets with the indexed by nu psi because it depends on nu and psi. So I take this 2 by 2 matrix, which uses psi, and then I form these two column, even and odd parts of p, and then even and odd parts of q. So here matrix acts on this column, and here I have an inner product of two vectors in C2. Okay, so I could write it down explicitly as a sum of 4 terms, but this is more visible if I write it like this. And then I integrate this with the measure nu. So this whole object, of course, this whole kind of inner product type of thing depends on nu and depends on psi. So now, as I said, let's view it as an inner product. It takes some effort to prove that it's a non-degenerate, but you can do it. And then you take powers, 1s, s squared, and so on, and then you apply Gram-Schmidt with respect to this funny inner product. Then you end up with normalized polynomials, q1, q0, q1, q2, etc. And they satisfy exactly like here, relation, three-term recurrence relation, with a twist that here you have a complex conjugation. Okay. So it should remind us of this eigenvalue equation that we had a few slides back, where let me show you. This equation where you had complex conjugation on the right-hand side. So here you have the same phenomenon. Okay. But in any case, again, we can reconstruct the coefficients of our Jacobi matrix from the spectral parameters through this Gram-Schmidt procedure and so on, similarly to the classical case. Okay, so let me state some open questions. In the self-adjoint case, the properties of the map from Jacobi matrices to measures is a deep and interesting problem in pure mathematics. So typically one compares sort of J, which are in some sense close to J naught. J naught is a standard Jacobi matrix corresponding to AN parameters being 1 and BN being 0. So this corresponds to orthogonal Chebyshev polynomials. So this, in this case, the spectral measure mu naught corresponding to J naught is just this explicit thing, supported on the interval -2, 2, and then one considers some sort of weak perturbations of J naught and asks how far is the measure mu from this measure mu naught. So, for example, a classical result is that if you have, imagine you have a Jacobi matrix which satisfies this condition. This basically says that, you know, Bn go to 0 sufficiently fast and An minus 1 go to 0 sufficiently fast so that this series converges. It's really a trace class condition on the difference J minus J naught. So in this case, take this measure mu corresponding to the Jacobi matrix J. It will have some absolutely continuous part, which we will write like this with the density F and the singular part. We throw away the singular part, and the absolutely continuous part turns out that it satisfies this condition called the Zergi condition. So this basically says that this density F cannot vanish too much. So anyway, the fundamental questions is what are the relations between spectral properties of J and the measures of this mu? And of course, in the non-self-adjoint case, it's one can ask versions of the same question. So how are the properties of this non-self-adjoint matrix J with complex elements on the diagonal related to the properties of this measure mu and the function psi? So we are just beginning to kind of scratch the surface of these questions. Finally, I want to describe briefly a work in progress, Schrödinger operators with complex potentials. Maybe for some people it will be closer to their interest, where the philosophy is pretty similar. So let me, this is just in one slide. Let's start from self-adjoint case. So imagine you have a Schrödinger operator on the half line with some real potential Q. You need to put some boundary condition at 0 for, of course, like Dirichlet or Neumann, something like that. So then such Schrödinger operator has simple spectrum, as is well known, and there is a spectral measure of this operator H. It's defined through this standard Weil-Titchmarsh M function. And Borg-Marchenko uniqueness theorem says that the measure mu uniquely determines the operator H. I'm deliberately using the same notation as for Jacobi matrices because it's a related object in this different context. So, so that's the classical self-adjoint case. And what we are doing with my collaborator František is we are considering the analog of this for the non-self-adjoint case. So we consider the same operator, but with a complex potential. It was quite a popular topic in the last couple of decades to look at spectral properties of these operators with complex potentials. But once again, we are not interested in the spectrum. At least our way of setting up the inverse problem is not about the spectrum of this operator, but more about the spectral decomposition. So we can define the spectral data again as a pair measure function, where this measure is the spectral measure of mod H, and psi is a function less than or equal to 1, defined almost everywhere with this nu. And we can prove that this pair measure function uniquely determines the potential Q, which is the complex, the analog of this Borg-Marchenko uniqueness theorem for complex potential. So this is work in progress, and so I'm not talking very much about it. Okay, and let me finish by displaying the photo of my collaborator. Okay, so this is also my colleague and friend Eugene Shergorodsky, but he has nothing to do with his work. It's just that I happen to have only one photo of František, which is in this combination. Thank you very much for your attention.